multi-marginal flow matching with adversarially run interpolants. So before we begin, let's read the abstract. Okay, so did you find any gap sentences? I think there is no very explicit gap. The purpose of this paper is to extend a method what is called flow matching. So they extended it to multi-marginal flow matching. So I will explain both flow matching first and then the multi-marginal flow matching. So in one sentence, the goal of this journal club is to find a flow that connects multiple snapshot data. So if you have this kind of multiple snapshot data, then from the method what is called by multi-marginal flow matching, you can find some flow. This paper deals with one theoretical background on this method. Okay, so let's begin one by one. So what is AI? AI is to run a function. So if you have a function with input and output data as follows, you want to guess what is f. Then the training data are input and output pairs. And from using the AI, well, I will not gonna in detail about this, you can estimate some candidates of f by noted by FNN, F neural network. And then you can guess when there is a new input 3, which is not in the original input data, you can get some output. So now what is generative AI? Generative AI is to find the distribution. So it is again a kind of AI. Now you have an input and an output like pictures. The input pictures are the real photos and the output pictures are animated photos. Then again, if you train the AI, in the end, you obtain the map between some distribution to the other distribution, which gives as follows. So original input distribution is the real photos, and the output distribution is a distribution of animated photos. So you run, in some sense, a map between this. At the end, after that, if you pick some specific sample, then you go through this map to obtain each animated version. So this is a brief concept of generative AI. But if you can formulate the generative AI in some mathematical language. So again, generative AI, the purpose of it is to run a target distribution. But again, so in order to understand it, we may have to know about the notion of push forward of a density. Assume that you have a map f from x to y. So this will be our neural network. And mu is a probability density on the domain x, okay? Or the measure, probability measure. So if you draw the picture, we have like this. Then we define the push forward. So we have a map f and we have an initial probability density. Then the push forward f sub mu is a probability density on y. So mu goes to y by the map f. And this is the formal definition of how to compute the push forward. If you put a subset A of the range y, then it is computed by the inverse map of f. So you put the subset in y, and you pull it back to x and compute using mu. So let's give an example. If you have a map on R to R, this is translation x plus 5. And if you want to put some probability density in this domain to the range, then it can be computed like this. If you put A, then by definition you have this. Okay. But F inverse 1, F inverse, what is F inverse? It is x minus 5. So you have this set, which is A, which is translated to the left by 5. Then we get this. This is a simple example. So if you illustrate it as a picture, you have an input measure. Then it's pushed forward by this translation. It will be just translation by 5. Like this. Then if you want to compute the probability or measure of this subset, you do this by pulling it back to the original measure. So why do we do this? So as I mentioned, generative model, the purpose is to run a distribution, but in order to say a distribution, you have to say where does it live in. So the set will be on Y, the distribution is on the set Y. Then, so why do we do this? Imagine you sample the pictures from the distribution. It means to put some element of this set Y. So mathematically, so generative AI is again a neural network. So you run a map from X to Y, but in this time you have a probability distribution in both sides. So this map should satisfy the following condition. If you put the probability density from the input domain, then it should be equal to density in the output domain. This can be formal definition of probability density, and it will be used in the method of multi-marginal flow matching. So I just listed the examples of generative AI. So for instance, there is normalizing flow, diffusion model, GAN, and with variation of to include something like that. Today we will focus on flow matching. Okay. What is flow matching? Flow matching is a recently developed generative model that uses flow to generate.
Okay.
Okay.
So what that means? I have to set with function from x u to the y coordinate. And then if we push for the u with the x theta, it should be the Everyone is okay about this? I think very clear definition of the generative model. Everyone is okay?
Yeah.
If you confuse, you should stop and ask.
So it can be illustrated like this. If you have a input distribution or source, you get the output distribution via the map F zeta. But here, the flow matching wants to obtain the map F zeta using the flow. So what does it mean? So you continuously, in some sense, transforms the input density to the output density using this time-dependent map. So its initially it follows the distribution mu, distribution, and at the end, which is time one, it follows the output distribution loop. So by the flow, it means that we want to find the ODE, which satisfies some equation like this. This X zeta should satisfy the power in ODE. And here UT is the vector field. So finding an ODE means to finding a vector field UT. And again, finding a vector field UT means that we want to approximate this using some kind of neural network to minimize this kind of loss, to approximate UT, the true UT by this neural network. However, what we have in practice is not the ideal case. We only have samples from the target domain like this. We don't have the full information, so what we can use is only this two. So initial information, we can set this freely, because this is our some artificial initial distribution, and we only have samples from the true target distribution. So we have to incorporate how to use this.
So theta 0 is original distribution.
Yeah, it follows original distribution.
Theta 1 is following the target distribution. And our vector field mu e. What is the subindex T of the loop?
So the vector field can depend on time. It can change.
Yes, right. Let's see. Depending on the time. We want to minimize loss. Here, UTX and UT data. Can you explain what is UTX and UT data?
UTX is the true vector field we want to approximate. This will be our neural network.
What is a true?
Actually, true is not unique. True is something that gives, we only have input and output. And true is something that gives, if you plug in input, then you get output. But it is not unique.
Oh, we don't know.
We don't know. We what we only want for this true is to start from input and finish at output.
Well, I'm a little bit confused about that. But that's not our actual loss. If we know the UTX, that will be our loss.
Yes.
Okay, because we don't know the UTX. I see.
We only have samples.
Oh, okay, that's right.
I also have some confusing point there. So here UT is also dependent on the AI-based parameter zeta because it came from the F zeta, and then the UT zeta is also looks dependent on zeta. So could you explain?
UT depends on zeta. Yes.
And then UT zeta is also dependent on
zeta. Where is zeta? Here it is.
뭔가 또 UT도 세타에 디펜던트하고 UT 세타도 UT 그냥 뭔가 차이가
UT는 dependent.
그래 yes.
Okay. So let's go this a little bit deeply. Before that, I want to explain you some two concepts, two ways to explain the same phenomena. So particle path is one thing and probability path is the other thing. So imagine that you have a glass of water like this, and you put some ink in here, and you make like this. So you want to describe the motion of this ink. So there are two ways to describe this. First one is keep track of, you look at the individual molecules of the ink, like this, the green one. You keep track of the individual molecule of ink. That means that you follow the particle trajectory. It means that you follow the ODE like this. So you start with the initial data, initial green circle, and you follow some ODE. Another way to understand the motion of this ink is look at the whole picture of the ink. It means to understand the distribution. Then this density of the ink can be described by the following PDE like this, which is called the continuity equation. Do you find some similarity in this ODE and PDE? They share the UX. So this vector field of ODE is here in the continuity equation.
So everyone is okay about this left side and right side? This is very, very important concept. So left side, you need a data, you track all the trajectory. But if you throw the ball, you have to tracking all the trajectory of the ball. The right side is just if you throw the hundreds of balls together and just look at the distribution of the ball.
Yes, please. Let me give you an example. So for instance, if you have some constant speeds motion, you will have a ODE like this. And if you translate it into continuity equation, you have this kind of. But if you solve the ODE with the initial data x0, you obtain this. But I omitted the detail, but you can easily solve this kind of PDE. This is a transport equation. So you will obtain like this. So the density at time t is obtained by the initial distribution. If you illustrate this phenomena using the picture, you have a starting point x0 and the initial distribution t0. Then in the ODE point of view, every single initial data just moves with velocity 2, green one. And in continuity equation point of view, this forward equation moves. Okay. Same. Okay.
Yeah. This is I don't know. Everyone, this is so important. You should really try to understand the philosophy underlying these two equations. This is a very, very big thing. Everyone understand it or not? Everyone is okay? So, what about, do you think this one, can you see that they are same or not? If the governing equation is left side, so left side means every second xt will be moving by 2. Left side, that is our understanding, is it? if we throw the ball is moving 2 steps every second, right? And then what is the meaning of the right side? After 1 second, our problem, the balls, if we have thousands ball, their ball distribution, this location of the ball distribution at time equal 1 is equal to the, initially we have ball distribution. And we're moving that ball distribution by x minus 2. That means we're moving by just 2. We throw the 1,000 different initial different balls, but exactly after 1 second, we're just moving by 2. What does tell us? Every ball is just moving by 2. Because without it, is it possible? We throw the really any weird shape of the distribution. It could be uniform, Gaussian, or bimodal, whatever. After 1 second, we're just moving by 2. This is only possible when 4 is moving by exactly 2. That's why they are equivalent. Up to here is okay. And then number 2. I know in up to high school or college, we only learn this kind of differential equation, right? So that you may be uncomfortable about this equation, but in real life, this is much, much useful. Okay, let's think about it. To do this, to use this equation, what kind of data set we need? Let's say here we have about 30 people. 30 people will throw the ball. Okay, so all 30 people, everyone has different power, different velocity, it's okay. Anyway, we will, no, let's do this way. Okay, let's do, anyway, we throw all the ball. Then what we have to do is, to do this, what we have to do is, there is someone who should look at his ball trajectory, everyone should track the ball. So every 30 trajectory, we need someone looking at the trajectory. Is it easy or not? It's not easy. But this one, what this means is, we were just looking at the initially, someone throw the ball at this position, someone throw the ball at this position. So we will take a group photo. Done. And then after 2 seconds, I don't know where this ball comes from. We're just looking, again, we will look at the group photo. Group photo. There's no individual trajectories in it. Which one is much easier to get? So tracking every person's or every ball's trajectory, or just looking at the group photo, which one is much easier? Yeah, of course. This is much, much easier data to get. Isn't it? So, for instance, let's look at height information. Tracking every Korean people's how their height or weight is changing time series data is easy or not? Very, very difficult. But let's look at just this year's distribution of height. Next year, just distribution of height. Which one is easier? Second one is much, much easier. That's why I know, although you are more comfortable about this equation, but why? We want to use this uncomfortable equation, because in real life, we don't have this kind of data set. In single cell, do we have? No. In biology experiment, usually tracking the trajectory is nearly impossible. You get it, right?
So, why did I say this? So let's go back to our problem. What we only have are the samples from the target distribution. So we cannot actually, we have no idea of this true or desired vector field.
So that is time dependent.
Time dependent.
You kind of the feeling we need actually two trajectory, but we don't have that kind of.
So how to incorporate samples to our target vector field? We used our just philosophy I just explained. So the situation is follows again. We want to run a vector field, but what we only have are the samples in target field. Sample Z. Again, the particle trajectory is trajectory following the ODE. You translate this now, we can translate this to the probability path which follows this continuing equation. But using the probability, you can think of incorporating the samples. So if you have, so our source will be, so input distribution will be P0 initial data, target will be P1 as follows. Now, using the samples, you can think of with conditional probability. So if you work with probability, then you can think of conditional probability. Actually, if you know the target distribution exactly, then you can reconstruct the original probability path using the following formula.
But here, P1 is the sample G is kind of 1 point.
Yes, that's 1 point.
Forget the 1 point. I think people will be confused about from the condition from sample G. Please explain the sample one more time.
Okay,
Yeah,
so
that's yeah. We have a sample G.
you have sample G, so it's something like this. Initially, in the original sense, you start with this distribution and end up with this P1, 14. Now, if you fix some sample G, then the probability path, conditional probability path, starts with the same input, but it ends up with a distribution which is concentrated in the sample. So this Dirac G. Initially the same, finally concentrated. So having this conditional probability path, now you can go back to the conditional vector fields like this. But what is this actually? We have to explain it. Okay. So then before that, let me illustrate it using the pictures. So here, this is the original probability path. You start with this mess and you end up these 4 complicated tiles. But conditional probability path, you start with the same mess, but you end up with this one one effect point, which is a sample. So now the original vector field satisfies this following ODE, where every trajectory at time t follows the distribution probability path at time t. Now I can define a conditional vector field. It is a vector field whose solution now follows this conditional probability path. So this is in some sense defined indirectly. This for ODE, solution to ODE follows conditional probability path. So it's really
목표가 정해져 있는 거죠.
네네, 종의 목표가 정해져 있어요. So initially, you start with the following distribution and end up with target distribution. And every point, you have a partial trajectory like this. This is original vector field. But now you have some fixed target like this. Every point will go end up converge to the center like this. And the vector field which describes this kind of motion will be the conditional.
Everyone is okay. 이제 think it's a very good explanation, but if you're confused, you should ask it. So I think this is very, very good also. So this is very similar to a class. Initially, every people begin from the Gaussian distribution. So the chance of you will get A, B, C, D, F, we don't know. Because at the beginning of class, everyone thinks that you will get an A. Right? But fortunately, at the end of semester, life is not that easy. Someone get the A, someone get the F. There is different group of the people, right? Correct? So there is certain trajectory there, definitely. But what that means is this red come from here. Okay, this is a D group. We want to know from the beginning. Of course, we don't, from this beginning, we have no idea someone who will be the D or not. It's not easy. But at least, if we look at the midterm, now we feel that, these people are heading to the where? B. Does it make sense? So that's the meaning of conditional probability of the D group. Kind of typically the people who got the D at the final, that group have a similar clustering at the midterm, isn't it? So usually they don't come to the class, they don't take a quiz, and there are several characteristics, right? That can be captured by this method. Kind of initially, they begin late in the class. That's one symptom, and then midterm score is not good. Then now finally no more homework anymore. Does that make sense? So this is so important, okay? 괜찮아요?
네.
네. 근데 이 이상 쉽게 설명해 줄 수는 없어요. 네, 진짜. 그냥 들어도 돼요. 네.
This example says that at time equal to 0, that x bar d and p what should be the same as
Yes.
source.
Yes.
Then always true or trivial thing, or do we assume that? So when in my previous seminar, we learned something extremely rich, and at that time we first matched 2 points in the source and target distribution. That means that under the condition of certain sample, that only some parts of the target source distribution could only they goes that point. So should we have some assumption or about that, or
I think we need to assume that.
이니셜 컨디션을 주자.
그러니까 G의 저희 컨디셔닝을 듣는 순간 제 생각에는
여기는 가정은 아마 초반에는 모른다는 가정이지 않나.
그거가 그래서 가정인지 트리비얼한 건지 가정일 것 같기도 해요.
그러니까 문제 셋업에 따라서 풀수
네,
있으니까.
쉐딩거 브릿지 할 때는 그때는 처음부터 그 최소가 되는 걸로 매칭을 하고 시작.
아, 그 G를 할 때.
네. 이 예시에서는 아예 그냥 노말에서 컨디션으로 가는 거 다 하는 거.
근데 이니셜 하게는 Z가 상관이 없으니까.
그러니까 인디펜던스를 가정하는 거잖아요.
네.
지금 여기 가정은 P0 분포랑, 그러니까 이건 이제 인간이 태어날 때 가능성 다 똑같다 가정하고 하는 거고, 슈레딩거 브릿지는 아마 지난 학기에 D를 받았으면 maybe.
그래서 플로우에 학습 잘 되는지 안 되는지가 저거에 따라 또 달라질 수 있다. 그거 어디서 본것 같긴 해요.
근데 아무래도 저거는 좀 성능이 떨어질 수도 있겠다는 생각이 드네요. 그러니까 이제 최종이랑 시작이 독립이랑 가정은 어떻게 보면 좀센 가정이긴 사실.
네.
근데 U의 그 슈레딩거 브릿지는 사실 최단 거리를 어떻게 보면 좀 더 리스트릭션을 주고 하면 좀 더 뭐 그럴 수도 있고, 그러니까 뭐 이런 거 아닌가? 그러니까 이 그룹으로 갈 애들은 아무래도 요 위치에 있는 애들이 확률이 더 높다 정도의 어떤 조건을 주는 게 슈레딩거 브릿지이지 않을까? 뭐 그러니까 이건 뭐가 더 좋다 안 좋다의 뜻보다는 그 상황이 맞는 상황이 있고 그 상황이 안 맞는 상황이 있지 않을까? 예를 들어서 뭐 잉크의 분포를 예측하는 거면 우리지 않을까? 시작의 분포랑 끝에 시간 한참 후에서의 분포랑 거의 독립이지 않을까?
그래서 저런 모양의 시작 가정하면
그러니까 잉크 문제는 독립이 맞는 것 같아요. 성적 예측은 독립이 아닐 것 같고, 초기 학점이 다른 게 한 문제마다 다르지 않을까 하는 생각.
네. 그럴 수도.
적어도 이게 더 쉽게 할 수 있을 것 같아요.
구현을 보시고
사실 나중에 인풋 분포랑 아웃풋 분포의 그 커플링이라는 걸,
거의 컴퓨터.
그 커플링을 또 저희가 정할 수 있다고 나오거든요. 커플링에 따라서 또 달라져.
그러니까 어떻게 보면 프라이어를 집어넣을 것인가 안 집어넣을 건가의 느낌인 것 같아요. 통계로 봤을 때. 그러니까 이거는 우리가 아무런 선입견을 안 갖고 보겠다는 것이고, 근데 우리가 경험적으로 어떤 지식이 있으면 커플링 펑션을 넣고 시작할 수도
네.
있지 않나? 네, 그럴 것 같아요.
Okay, so let me go into a little bit more. So we have a original marginal vector field and the conditional vector. So it is theoretically proven that if you have a conditional probability path, and you define conditional vector fields using this conditional probability path that I just explained you, and you assume this. Then you obtain the trajectory which follows the conditional probability at time t. Then actually, if you define this vector field, so now you start with this, not you don't go from this from conditional vector field. You start from conditional vector field and you define ut. If you do this, then actually this generates the true marginal probability. Okay, so it means that if you solve this ODE, then its trajectory actually follows the true probability path. This just just to convert. So you can skip it if it is too much. And if you are interested in flow matching, you can study this lecture note.
Could you let me know what is
Yeah.
the P data?
P data, the distribution of the output. The true output is
And it's different to the distribution written by Gaussian topology.
no, it's the whole thing. Okay, so conditional vector fields. Now, so our problem is that we only have samples from output distribution. Now we define a conditional vector field. So in order to use samples, we use conditional vector field.
So, can you remember? So, anyway, the key point is if we find the conditional probability F, then if we sort of give a weighted average, then
Yes.
it will be real kind of general PTS. That's the key point.
Yes.
So we learn the individual and then we merge it.
Yes.
Then it will be the original.
Yes.
So that's the key
Yes.
message for this. Does it make sense? Okay.
But one misunderstanding can arise.
Hmm.
So anyhow, even though we are focusing on the flow, our original purpose is only input and output at 0 and at 1. So the shape in between is not really matter. So we only need to generate the correct target. Okay? So that is why we define it in this kind of particular way.
It doesn't need to be unique, I guess.
No.
No unique.
No.
Okay.
Okay, so again, our goal is to go from input to output. Okay. So first we have samples from output distribution. Now we can take a conditional probability path and the conditional vector field. So this is in a picture. You start with this red circle. You have samples, and the targets are the surrounding 5 circles. Actually, you take only one sample, the red dot here, and you run some vector field. But at this moment, there are, as Professor just asked, there are many choices of the conditional vector field. For instance, one can take time-independent vector field. So if you have initial point and the final point, you can just take some linear velocity, constant velocity, and it actually is related to the optimal transport of flow matching. And there are some other ways to take a conditional vector. Now, using these samples, you can construct a neural network parameterized by this setup. Then now we can construct what is called a conditional loss function like this. So since we set our conditional vector field here in step 2, now we have a target. We will minimize using this neural network to approximate conditional vector.
Can we just think that then this neural network will be nearly the same with the z minus x?
Yes.
Because we can just think that we have a neural network which is equivalent to z minus
Yes.
function.
Yes.
Okay.
Actually, I have to make a comment. For those who are familiar a little bit with flow matching, it is not really equal thing with optimal transport. This is optimal transport is one particular way of doing flow matching. So we matched conditional flows, conditional vector field, but it is not our true goal. Our true goal is to, in some sense, find some true marginal vector field, which is to minimize the following flow matching loss.
Without G.
Yes, without G. But what we actually minimized is the conditional matching loss. Does it help? Is the problem. Actually, it is theoretically proven that minimizing this conditional loss function is equivalent to minimizing the original loss function flow matching. That is to say, their derivative with respect to the neural network parameter are the same. So if you imagine you do the gradient descent, you use the derivative, but their derivatives are the same. So minimizing one thing gives you minimizing the other thing. So again, if you have a conditional vector field like this, if you succeeded in minimizing this loss function, but once again, you have to do this with many samples. Doing only with this doesn't give you anything. Then actually you can obtain this following flow, desired flow to the target distribution.
Can I ask a question?
Yeah.
Actually, the theorem, I want to understand that the theorem minimize is equivalent to the depth one. For my question is, for any the Z distribution, any data, is it possible? How possible that equivalent? If we have some data set, it's it's a 100 or
I mean,
1,000 like that.
here, theoretically, you assume that you know every samples.
Exactly.
Yes.
You know every sample, then
Yeah.
it can be awesome.
Okay. So far is the introduction to the flow matching. Okay. I will find everything. Is it okay? Okay. Actually, one thing to remark is that flow matching, the flow in flow matching is not the real flow. Assume that you succeeded in finding a vector field which matches the input and output distribution. So let's say that this is a distribution of happy people, and we want to go to the distribution of unhappy people. So you performed flow matching on these two distributions, and you get the flow like this. But can we believe that this learned flow has any meaningful message? For instance, if you consider the intermediate step, does it give us any information? This is the question. But actually, I think no, there is no meaningful information.
Kind of the one reason is the flow. Basically, we assume that what is the optimal transport? We just follow that linear line.
Yes.
Kind of if let's say this is happy or unhappy. Let's say healthy people and Alzheimer's disease people. And the trajectory from the normal to Alzheimer's line. And the shortest line in this XY axis we define is not, of course, trivial.
Yeah. So it's somewhat misleading if you argue that you obtain some true flow using this flow match. Yeah. So now, but if you have some additional information, you can say something more, and this is the topic of our present paper. Okay, so yeah, so here there are probability densities, but if you think the space of probability densities, then it can be denoted as just a point in that space. Then by the flow matching, there can be many choices of starting from P0 to arrive at P1. So there are many ways to arrive. Sometimes if you do the optimal transport, it inserts line, and sometimes you go in different way. Okay. But what if you have some additional information in the intermediate steps? So if you have initial and final distribution, if you know that you have some intermediate information, can we adjust our flow to smoothly connect these intermediate steps? One easy solution is the following. So we have this kind of step. You do flow matching here, and here. This can be a easiest answer, but this flow can be a piecewise smooth, really smooth. So it might not be ideal. So that's why the authors try to think about some way to do this. It is called the multi-marginal flow matching using GAN. So these are just notations. Time steps T1 to Tk. We wanted to dot Tk 0 to 1. And at that time steps, you obtain some distributions. Sorry, this will be P, not Q. PT1, PT2, and PTK. For instance, one choice of conditional vector field can record that initial point, final point. If you have initial and final point, then it can be some linear constant velocity. So here, the initial point is sampled from the initial distribution, and final point is sampled from the final distribution. But you can observe that actually this is a time derivative of this following quantity. Right? But can you guess what this is? Yeah, and actually interpolation between and X. So that's why it motivates us to define the interpolant input output at time t, like this. And here, actually, this interpolant is a solution to the following ODE, where the vector field is this conditional vector. Okay. So if you have 2 points input, starting and final points, then interpolant is really some. In this case, this is straight line, but some line in between. And the vector field notation is wrong. Basically, this direction of this fine G curve. Okay, so the message is that the time derivative of interpolant gives conditional vector. Okay, so why do we do this? In a original flow matching, you have samples from input and output. And for instance, if you take the optimal transport, constant conditional probability vector field, conditional vector field, the interpolant is defined just like this, where the conditional vector field is like this. Now, the multi-marginal flow matching, you furthermore have some intermediate data. And not only just x0 and x1, we have some intermediate time steps, xti. Then you somewhat adjust an interpolant by adding this so that it can smoothly cover the intermediate steps. F5 is, this will be a neural network parameter. Can you guess why there is t and 1 minus t factor in front of this?
Only working during the middle.
Ah, yes. So this is to ensure that if you put t equals to 0, then you have x0, t equals to 1, x1. Intermediate. So now the constraint that the flow goes through the intermediate step can be written using the push forward like this. But here there is some strange looking formula and it's a bit tough. But anyway, I will explain it on the next slide. So now you have a constraint by a formula. I mean, you know about this. So this is a probability density, and this is a probability density. Even and neural network. So this is again some kind of generative model. You have to match to this distribution. And the authors try to tackle this by what is called GAN, generative adversarial network. But what it is, I will explain it in one slide. So what is this constraint? Let's see for our particle and density correspondence. Particle trajectory can be translated to probability path. Actually, given an ODE like this, you can define a flow map like this. T, the input will be some value in the space where X lives in. If you put some initial data, it can give us its motion at time t, following the ODE. This is the flow map. Okay. If you record the differential equation lecture. So this is a map from RD to RD. Then, if you push the initial distribution, which lives in RD, then it can go through this flow map and gives us the distribution at time t, which follows its probability path. This is called the representation formula of continuity equation. So can you feel the similarity? Now let's record the interpolant. So initially it is, if you put t equals to 0, then you have x0, and t equals to 1, then x1. And you have, and you record that actually this is also a solution to this ODE. So some similarity. And actually using this particle density correspondence, this ODE can be written as this, where the flux is conditional method. And unlike this flow map, now you have two inputs, initial point and final point. So RD times RD goes to RD. But anyhow, you push some density in RD times RD and obtain a distribution at time t. In the same way, it can be a bit tricky. Where here the phi is called the coupling of two density, but I will omit the detail. Too much. If you are too complicated, can be typically set by a joint distribution of initial and target. You know this.
저쪽에 있어요. 알테스. 저기.
Phi is a probability density on two variables. This times is that you simply have this multiplication. So in some sense, they assume the independence that Young mentioned. Anyhow, we understand this formula. We have to add a constraint on our neural network. And how do we do this? We use GAN. So GAN is a generative adversarial network. It consists of two parts. But anyhow, it is a generative model. So yet another generative model. You want to generate some samples, target samples. In other words, as we just studied, it wants to study a map f zeta, which gives you, if you push the initial distribution, you obtain the target distribution. So in other words, generate an object that looks like real. So GAN tries to generate an image. First time you keep generating a fake images, but if you train the neural network, you end up generate something that looks really like a real. So in other words, you generate that cannot be discriminated from two. So that's why we have generator here and discriminator. How do we train this? First, you have a generator. Generator, you start with some input distribution and generate some fake image using this net tree. And second, you have a discriminator. So discriminator tries to designate a probability of 0 to 1 value of this input. So now for the generator, what generator wants to do is to generate samples that looks like real. So this G of G is a sample that the generator generated. And if you put it to the discriminator, it should ideally converge to 1, so that it is high probability. High probability means high reality, more realistic. On the other hand, the discriminator wants real image converts to 1 and fake image converts to 0. So it wants to discriminate real and fake image. In order to jointly train it, a typical way to do this is to use the min-max GAN loss function as follows. So first, you fix a generator G and try to maximize the whole thing using this discriminator by varying this discriminator. Why this is maximum? If you want to maximize this log dx. So dx is from 1 to 0 to 1, and log function looks like this. So this part should converge it to 1. So this should enforce this part, real image to 1, and this should convert to 0. So fake image. In having this, the generator should try to minimize the whole loss. So this is called the min-max GAN objective.
So,
Okay.
Hello. He is this. You will use various discriminator.
Yeah.
Type from the
Yes, trained.
So if you look at the blue, there is several discriminator, and using that several discriminator, we some discriminator performance is bad, some performance is very good, some performance is very good means that expected value is large. But our GAN generator want to do is they want to minimize that maximum performance of the discriminate.
use this.
Is it clear about this index?
So the authors applied this again to employ this constraint. So using the min-max scan objective, I just copied the formula I showed you before. They try to impose this condition again. This is just the same. B is a discriminator with neural network parameter. And G theta is G5 is the interpolant that I defined. And this is the gain loss. Okay. So the whole architecture in a brief 2 sentences is the following. You first train the GAN to match this constraint condition. Then now you perform the flow matching using this interpolant. So you minimize the conditional flow matching loss and you obtain the true one. So for instance, if you have a snapshot of data, which is like this dotted one, and although the picture looks small, but here is t equals to 0 and t equals to 1, so which are the input and final point. Then using this adversarial interpolant, you obtain some, in some sense, some nice flow. Whereas the original optimal transport based flow matching, they are quite okay, but it seems better.
What is the blue and red?
Red is the true snapshot
Real data set.
and yes, and blue is the probe.
Oh, you see. Okay, so everyone is okay. So this is your initial starting point. This is our final. Where is final destination? Final destination is here. Okay. Here. Then we give a snapshot here. So, and then this color means the time. So we know that, and this is time.
If you look at this piecewise linear, it means that that I just mentioned before. So if you have multiple points, you do flow matching, flow matching, flow matching. This is piecewise linear. And cubic spline is another method of multi-marginal flow matching, but they still use some kind of spline, like a polynomial regression in numerical operation method. And now they use in okay, so this end.